Everybody, welcome back. We've got a great presentation coming up. I'd like to introduce Noemi Derzsy, who is currently a postdoctoral research associate at Social Cognitive Network Academic Research Center at Rensselaer Polytechnic Institute, and proudly to say she's also a NASA dataNaut. She holds a PhD in physics and research background in physics and computer science. Her interests revolve around the study of complex systems through data. Noemi's work spans from analyzing and modeling cascading failures and controllability of systems with underlying network structure to studying the modeling social systems and criminal activities from real-world data. As a NASA dataNaut, she uses network science and data science techniques to tackle problems using the openNASA data. Noemi Derzsy.
Thank you so much. Hi, so I don't know how many of you have been here yesterday when my dataNaut colleagues talked about what it means to be a NASA dataNaut. So I'm going to start for a few minutes to talk about that. So NASA dataNauts is an initiative of NASA that started in 2015. What they do is each year they select 50 people to engage the community to work and collaborate on openNASA data. And we have many activities. We have weekly webinars where we share each other's work. We start to collaborate on different projects. We come up with project ideas of what we can do with openNASA data. And so NASA is trying to build this connected community of not only data scientists, but also artists, programmers, and everyone who wants to get involved in openNASA data. So I am also a NASA dataNaut, and I was selected last year. And this is basically a volunteering work, so everything that we do is off work schedule. So, but we are trying to engage as much as we can other people and get them to know about this program. Initiative. I organized an event and I was warned that it's not program, it's initiative. I don't know what's the difference. Anyway, so about openNASA data, if you go on the platform, open.data.gov, you're going to see that NASA has posted publicly available 32,000 datasets. You can find more than 300 code repositories, which you can play with. And they also released 51 APIs, with which you can access the datasets and play with them. So if you want to start and work with it, basically what you need first is you need to obtain an API key, which you can obtain from this platform, api.nasa.gov. And here, if you look on the left, you have API key sign up on the left, and from there you can enter your email address and you will obtain a key, which I coded. And using that key, you can start scraping data from the openNASA dataset. So what one of our colleagues, the title is not visible, one of our dataNaut colleagues, for those of you who use Python, developed this PyNASA package, which you can just pip install. And it will give you already several of the data sets that are available. And this is a continuously growing package, so you can find it on GitHub, and you can work with it. So what can you do? So the titles are not visible on my slides. Anyway, so this is a meteorite landing data set. The visualization I got from the website because I found it really nice. So NASA posted publicly available the meteorite landings, and from 1988 till present, and it's continuously getting updated. And what you can do is you can check the locations, and you can visualize it on a map. You can check the impact. Oh, sorry. Other things that you can do, you can do deep learning projects if you're interested in more sophisticated projects. So there is a vast collection of images collected from satellites and Hubble telescope. This one is, for example, APOD. It's an astronomy picture of the day. Each day you get a different picture. And with this you can do all sorts of analysis. Similarly, there is the EPIC, which is a different collection of image data sets. This is also this is from space images, and you can also analyze different things on this. And what else you can do? So you can do data visualization, data analysis. For example, there is the NASA patent portfolio, which you can analyze and see what patents NASA has. You can do deep learning, as I presented earlier, because there are those Mars rover data sets collected by Mars rover. And they also have, in addition to images, you also have sounds. And this I copy-pasted from the website because I found it funny. So when we retrieve sounds from far-off planets, we can apply the filter to identify unknown human space colonies. And that was a joke, but sort of. So what else you can do? You can have hardware projects, art projects, educational projects, whatever you can think of using openNASA data. And there is also on the platform a blog where you can actually post what you did, and if it's exciting, it's going to get on the website. So on top of this, you can also work on anything else that you want to. So why my interest in openNASA data? So I'm going to talk a bit about my background. So I have a PhD in physics, but I never really did pure physics. I started working on social systems as an undergrad. I started analyzing email communication networks, and then started using government data to analyze income and wealth distributions. And so I always use data to study social systems, and not only. So any complex system which can be described by an underlying network structure. So basically, if you can think of any complex system where the elements can be connected based on a relationship, then we are already talking about networks, and we can study it within the means of network science, which is an interdisciplinary field, because networks are everywhere. So networks, this is a Facebook friendship data, and I'm going to show you some basic network properties. So hubs are the nodes that are most densely connected, that have the highest number of connections. In this particular network are these. And then we define clusters, which are densely connected communities, which is the number of nodes that are more densely connected than the rest of them. Then we can define link direction, which we can talk about undirected network if we consider, for example, Facebook. There, if you're a friend of mine, I'm a friend of yours. However, on Twitter, I can follow you, but you don't have to follow me. That is going to lead to a directed network. And based on the link direction, we can analyze from different perspectives the network structure and topology. And the link weight is going to give us, we define a link unweighted if we say it's either connected or not. Or if we are interested in the strength of the relationship, let's say I'm looking at mobile communication networks and I want to see how many times I'm calling you. So if I want to see in the friendship network, based on the mobile communication network, with who I am more strongly connected to, then I'm going to assign weight to the links and say that the weight is going to be proportional to the number of times I called you or you called me. And if I'm not interested in the strength of this connection, I'm just going to say that it's unweighted, so it's either I called you ever in my life or I didn't. So these are some basic features that I presented, and there are many other characteristics that we can use to analyze networks. And if we look here, again, the title is not visible. So these are the applications, the fields where we can apply network science. We can use friendship collaborations, infrastructure networks like the power grid systems or computer networks, or other communication networks like what I said before, the mobile communication, or we can use it in politics. I'm going to show us an example a bit later, or any other system where you can think of the elements being able to be defined by a relationship between each other, then you can already construct a network. So this is an epidemic disease outbreak analysis done by a group in 2009 when the H1N1 virus broke out. And what they used is they used airline traffic data, census data, and transportation data, and they created this network model which could effectively predict how the virus is going to spread globally based on airline transportation, population, and human commuting. So if you are interested, I included the website. They have the software, and you can actually play around with the information and see how you can model the epidemic spread. So other applications of network science, for example, we can have, there is a human disease network where we can see the higher, the more densely connected diseases, and we can see which one impacts more the others. Unfortunately, the size doesn't really help here, but if I go, so this is diabetes, this is deafness, and then you can analyze the relationship between them. Another application that is analyzed by biologists is gene regulatory network and protein interaction networks. And there are other analyses on brain networks using the brain fMRI data. They study the brain structure and function by mapping it as a network of neurons. And this is, for example, a simulated brain network of 3 million neurons. And they study different diseases on how they spread and how they can be prevented. Another application is using the power grids that I've told you about. So power grid systems have this characteristic of when one node fails, they are going to trigger this cascading failure of successive failure of other nodes. So what happens is when a node fails, the load have to be shifted to the neighboring nodes. And then if those nodes have a lower capacity than what is given to them as a load, then they are going to fail as well. And as you can see in this animation, this is for the European power grid system. One node fails, and you can see in the yellow lines are going to be the successive failed nodes. in the network. And this is not only in the power grid, the same can be seen in other interconnected systems, like biological systems, financial systems, in the trade market. If one company goes bankrupt, it's going to affect the others. And also, it is a very important research topic, because power blackouts can cause high financial losses, and they can also have life-threatening effects. So other network applications is the 9/11 terrorist group. So they are actively analyzing terrorist groups, and not only gangs as well as network. Sorry, I'm not used to this. So in the figure in the left, you can see that this is the 9/11 terrorist map. And what they saw is that each hijacker was within 2 steps of the 2 original suspects that they uncovered back in 2000. But, and this metric was revealed by, so you can read more about this here. So basically, with this, they can use some preventive measures if they know the social network of these community of terrorist groups or other violent gangs. Then they can actually map them and see who they have to eliminate from the network in order to disintegrate the system. And then there is another example of defense, how the NSA uses social network analysis to map terrorist networks. And what else? So this is the World Economic Forum, and this maps actually each risk and how they are interconnected with each other. And the larger the dot, the higher the risk. So the highest risk reported by the World Economic Forum is the severe income disparity. And what we can see here is that how they are interconnected with others. And we can also analyze this as a network perspective. And other analysis, this is the global language network. And this uses data from Twitter, Wikipedia, and UNESCO book translation. And they study the importance of languages and their impact using network relationship. And here you can see the network structure and how it actually looks for each data set. And to move on, yes, friendship, just give me a second. It's the friendship network, which studies the happiness paradox, which says that most individuals in social networks experience the so-called friendship paradox. They are less popular than their friends on average. And it actually turns out that is indeed true. And you can read more about this paper, more about this study. I listed it there, probably since it has been published too. So this is a collaboration network. This was actually done by me as an undergrad. So here we studied, we obtained the Erasmus Scholarship network for year 2003, which is a scholarship in the European Union. And what we wanted to see is what is the collaboration between universities based on the number of students that they send from one university to the other. So what we did here, we highlighted the 5 most densely connected universities in Europe. And I remember when I gave this talk somewhere in Portugal, someone said, oh, of course, because those 5 universities are in a city that are in cities that are known to be the highest for partying. And that's why students chose that. So then we started analyzing to see whether if it's like that or not, but then we found out that actually it's based on what the professors choose and how they are connected, so it's not the student's decision. So then we also showed that the top 10 universities with the highest number of connections are these 10 in hierarchical order. And yeah, so there are many interesting things you can do and also many fun things you can do with network science. For example, this is the from Twitter data. We want to see who connects the funny universe, meaning which comedian is the most popular one. And as you can see here, the answer is Dave Chappelle. I still need to see him live. And other thing like Oscar award race, Hollywood celebrity network using Twitter data. And now I'm going to actually show, yes, opinion influencing and politics in social networks. So this uses Facebook data, and what they do is study the spread of opinions in social networks. And this is a very important analysis because you can see that if you strategically select smartly the same number of nodes, so here and here, you have the same number of nodes as initiators who you want to go out and spread the information about something. And then as time evolves, you can see that on the network, they spread the information at a different rate. And you can see that one is substantially better than the other. So then this is a big study about how to optimally choose the smallest number and the best number of nodes in a network such that you spread out your information fastest. Because usually these things come at a non-zero cost. If you want to pay people to, for example, product marketing, you want to have these influencers who are going to promote the product for you online. And then you want to pay as less people as you can and get the maximum benefit. So you want to obtain this. And you have to know which is the smart way of choosing that. And that is where network science comes. And to rescue. And then there is online communication between left-wing and right-wing political blocs. So here this is from 2009, and I'm sure this time wasn't any better either. So you can see basically that there is almost a complete divide between the two groups, the ones who are Republican and the ones who are Democrat. And there is a small bridge, but the rest of it looks like it's an echo chamber. If I'm going to group with the people that are thinking like me. So how does this all fit in network science, in openNASA data? Well, there is this openNASA data collection, and as a NASA data node, our project is one of the projects that I chose because it fits into my topic, is topic analysis to understand data associations. So this comes because NASA wants to see what are the important connections between NASA datasets and other datasets that are coming from other US government agencies. And NASA also wants to be able to effectively summarize the search for its data concepts for people who are not familiar with these terminologies and jargon. And for this, they started working on data dictionaries and developing open source taxonomies and ontologies. And what we want to see is how we can connect and associate terms in different dictionaries so we can actually unify the whole data. And then we want to see how we can investigate relationships between terms within various dictionaries and see if information content can be determined by comparing these to the relationships seen in other terms. So I'm running out of time. 5 minutes. Okay, I'm gonna run. So this is the collection of dictionaries and taxonomies. You can find it on GitHub, made openly available by NASA. And then the other thing that you can find online is open government data, which contains the 32,000 publicly available data sets. And this is in a JSON format. And the information that it contains title, description of each data set. It contains keywords. And these are also given, of course, given by each agency that actually works with that data. And these are keywords given by a person, so they are prone to error and misinterpretation of data. So this is how it looks. Oh, I forgot to change yeah. So basically, it's going to be a dictionary of dictionaries where you have 32,000 data sets. And what I started to play with is word clouds, because I wanted to see what are the most frequently occurring word clouds, and this is for the title of the data sets. So for the 32,000 data sets, these are the word clouds for the titles. And of course, I made them in the shape of rocket and spaceship, because NASA. And I also wanted to check the same thing for the descriptions. And here we can see different words that appear. It's land, earth, and data product. And if I'm looking for the keyword, oh yeah, this is also for the same thing, but I played along a bit more with the visualization. And I also checked the same thing for keywords. And here we can see for keywords similar visualizations. And then, of course, this is not very informative. We can see that the words that occur more frequently are going to be with bigger fonts, but we don't really know how much bigger. So then we are going to do term frequency, and here we can see the top 25 most frequent keywords, and then top 25 most frequent words. How much time do I have? And then, so I can go back a bit then, so you can take a better look at this. So yes, so these are the top 25 most frequent keywords, and we can see it's very Earth-oriented: ocean, land, biosphere, atmosphere. So these are the description, and this is for titles. For titles, we see projects that are not very informative for people who are not working on them. So we can also do word co-occurrence analysis to analyze which words co-occur in the same text. And for this, we can build a co-occurrence matrix, but I'm going to skip this because, yes. So, and then the idea is that what I would like to do is to build this network, which is a bipartite network, which means that a graph whose vertices can be divided into two disjoint sets. This is from graph theory. So what it means is that I want to have a bipartite network of keywords and words from descriptions, where I can create two disjoint networks. One would be a network of keywords, where I can analyze which keywords occur together based on the term that they co-appear in certain description. And then the other way around would be that I would connect two terms if they are defined by the same keyword, even if they don't appear in the same data set. And then, so this gives us two separate interpretations of the network. And then I want to analyze this depending on the weights that I assign. do I want to see how many times they occur together, or I just want to say that if two terms occur together using the same keyword, then I already establish a connection. And then this can be analyzed in great detail and through network science, and I also started scraping other open government data, and I want to see that the words that occur in the openNASA data in association with others, how do they occur the same words in other open government data. And I'm going to wrap this up. Yes, so soon I'm still working on this, so I'm going to post this on GitHub. The link is not visible, so never mind.
Question for Naomi? I do have one question for you. Great. You know, I'm a big fan of network analysis and network science. So I was kind of curious if you thought about doing something similar based on the NASA data notch, connecting the network analysis with all the NASA data notch past and present, how they're connected to each other, how they're connected to their expertise, and maybe how they've connected out into industry to not only find out what you learned from NASA's data, but how you're learning from each other.
So something similar that you showed with the people who attended your event. Yes, it's a good idea. I haven't thought of it. So we currently are 100. So it would be a 100-node data network, but it certainly can be doable, and it would be nice to see. Yes.
All right, thank you very much.
Thank you.